มนุษย์เราเริ่มตั้งคำถามเกี่ยวกับกลไกการทำงานพื้นฐานของธรรมชาติมาตั้งแต่ครั้งโบราณกาลองค์ความรู้ที่ได้ถูกส่งต่อจากรุ่นสู่รุ่นถูกพัฒนาปรับเปลี่ยนต่อยอดผ่านการค้นคว้าทดลองตั้งสมมติฐานและพิสูจน์ทางทฤษฎีเพื่อให้เข้าใจถูกต้องมากขึ้นฟิสิกส์ทฤษฎีถือเป็นวิทยาศาสตร์พื้นฐานที่สำคัญอันหนึ่งที่อาศัยแบบจำลองทางคณิตศาสตร์ในการไขความลับความเป็นไปของสิ่งที่อยู่รอบตัวเราตั้งแต่ระดับอะตอมไปจนถึงระดับจักรวาลส่วนหนึ่งของผลสำฤทธิ์ที่มนุษย์ทำความเข้าใจธรรมชาติผ่านภาษาทางคณิตศาสตร์คือเทคโนโลยีอันหลากหลายที่อำนวยความสะดวกในชีวิตประจำวันไม่ว่าจะเป็นโทรศัพท์มือถือคอมพิวเตอร์หรือแม้แต่โครงข่ายอินเทอร์เน็ตที่ทำให้โลกอันกว้างใหญ่แคบลงไปเพียงปลายนิ้วสัมผัสยังมีคำถามอีกมากมายที่เรายังตอบไม่ได้ทั้งหมดเกี่ยวกับธรรมชาติซึ่งถือว่าเป็นเรื่องที่ท้าทายและรอคอยให้นักวิทยาศาสตร์เข้าไปค้นหาคำตอบในอนาคตในปัจจุบันบุคลากรของวิทยาลัยเพื่อการค้นคว้าระดับรากฐานถือได้ว่าเป็นส่วนหนึ่งในการค้นหาคำตอบของคำถามข้างต้นผ่านการทำงานวิจัยหลากหลายที่ให้หัวข้อที่ล้ำหน้า
Okay, good afternoon, everyone, and welcome to IF Colloquium Online Seminar number 4, organized by the Institute for Fundamental Study, Naresuan University, Thailand. My name is Circulate Yukong. I am IF Deputy Director of Strategy, and it is a pleasure to welcome everyone to this afternoon online event. Well, let me give you some idea why we want to do this activity. Well, normally, most of the time, academic conversation would normally circulate among the scientists. Yet, bridging the gap between the science world and general audiences is very crucial for the country in this current competitive world. Then, the Institute for Fundamental Study would like to provide a platform for people who are interested in physics, mathematics, and other related fields come and enjoy in the progress of advanced research. For this talk number 4, we are very pleased to have Dr. Sucharit Takun, from Chiang Mai University to give us some idea about an overview on 2D materials. But before that, let me spend a little bit more time to introduce our speaker formally. Dr. Sucharit Takun completed his bachelor degree from Chiang Mai University, and then he went further for his master's degree in physics at Duke University, USA, and PhD in physics at Case Western Reserve University, USA. At the moment, he is working as lecturer at Department of Physics and Material Science, Faculty of Science, Chiang Mai University, Thailand. His research interest is on, I believe it's on the topic on exotic property of 2D material. Correct me if I'm wrong. And the talk will be roughly 40 minutes long. Before I stop doing the talk, if you have questions, you can put them in the comment. Our staff will collect all the questions and deliver to the speaker at the end. Anyway, without further ado, let me give the screen to our speaker, Dr. Sukrit. Please, screen is yours.
Thank you very much. So thank you, Dr. Sukrit, for such a nice introduction. So I am Sukrit Sucharittungu from Chiang Mai University. And today we will go over a topic of an overview of 2D materials, and which is I'm highly honored by the Institute of Fundamental Study to have me here, and it's lovely to be here again. So here's a little bit of the outline of my talk. So first of all, I'm going to go over the introduction of the things that are going on and 2D materials and some ongoing research in the flavor of the field that I work in. And then we're going to go over the graphene, which is like one of the fragment materials, and then a bunch of other stuff and some potential applications in different platforms. So a little bit about myself, as Dr. Sukrit has already given a nice introduction to. So I did my PhD at Case Western Reserve University as a PhD student from 2012 to 2017. And my work was mostly on the two-dimensional materials, as you can see here. I work on the indium selenide, tin sulfide, vanadium pentoxide, and then the research interest really sparked me into the field. So I did my postdoctoral research from 2017 to 2019 at Riken in Japan, where I built an STM chamber. The STM is a scanning tunneling microscope where you put a probe and then you create the quantum tunneling onto the surface of materials, then you bias it, and then you can actually find the distribution of the Fermi levels and etc. in the materials to get a band diagram. And then afterwards, I got the position as a lecturer from 2019 along with the COVID that came to Thailand. So then I continue research in the field of the low-dimensional materials, such as the growth of the two-dimensional zinc oxide in the electrochemical process, which is like pretty cheap and pretty easy to make. And right now we just got a few publications on quantum dots, where I work on growing the materials and make them part of the perovskite solar cell, which is the main research of the laboratory that I am part of. So first of all, when you talk about the 2D materials, whenever I run around and talk to them like, oh, hey, I got a PhD from 2D materials, people would say, hey, oh, 2D, it means like manga. It means like, if you talk about the Japanese pop culture, he would say like, oh yeah, two-dimensional girls and two-dimensional stuff. So yeah, well, I am also into two-dimensional stuff like that, but also I'm really into two-dimensional materials as a physicist and other things. So what brought the attention of the world, the scientific community, into the two-dimensional materials is, as you all have heard, is the origin of the graphene. And the graphene is one of the first few materials that you could actually make it cheap and then peel it out. So graphene is actually a two-dimensional form of the material called the graphite, where it is like hexagonal form of the carbon atoms connected to one another really tightly in a plane. But then again, among the different planes, they are attracted with a very, very weak van der Waals force. So with this such weak force, if you imagine, if you describe things with the pencil, you can peel like the thick black layer that comes out, right? So that peeling is also the van der Waals force being so weak that you could just crack like layers of graphite and then make them into pencil like really nicely. However, in general, like pencil are generally way too defective to actually create the graphene. So we would have what you call the HOPG, like highly ordered graphite and stuff. So again, if you talk about a statistical mechanics physics inside of it, so if you have learned some of the fundamental stat mechs, you would know that the distribution and the density of state would be completely different based on the different kind of dimension that you talk about in your system. So for example, if you talk about the three-dimensional materials, which is what we generally see is the density of state, aka the number of the electron that you would be able to put in a certain amount of energy, would go as e to the half, right? So now if you go to a 2-dimension, then the density of state would change as a flat line, and then if you go to 1D, then you have like a spike that comes out. So all of these could be derived fundamentally using a very basic statistical mechanics. So you may ask why people are so interested in 2-dimensional materials. So as it turned out, graphene is among of the most early easy access material that you could just like buy a highly ordered graphite and then peel it out using a Scotch tape, because the Scotch tape actually has like some chemical bond that could pull out the layer of graphene, and then you can clean it using acetone and other lab equipment, which is very cheap and very accessible. And Novoselov and Gaim, these two guys, when they first worked on the material, they were not working on graphene. They were using carbon substrate. They were using highly ordered graphite substrate to grow something else, as it was rumored. So basically, after they use the graphite substrate, they need to clean it. And after cleaning it, they start peeling things to like, oh, okay, I need to scrub out this material to reuse this expensive substrate. And then turns out that like, hey, there's some black stuff that's stuck into the Scotch tape. So they start looking at it under the microscope, and then they're like, oh shit, we discovered something really nice. and so here comes the graphene. However, so you know that I kind of spotted earlier. This is Mr. Van der Waal. So Van der Waal is the force that describes the pulling between the different layers here, which is significantly weaker than the bonding that the graphene shared in the layer itself. So from there, by pulling things with Scotch tape, you can just peel it out. So let's consider what we have right now. So if you consider a two-dimensional sheet of graphene, why is it so interesting? So there is solid-state physics fundamental problems called the tight binding approximation, where you approximate the wave function around a very tightly bound core, and then you could generally derive what you call the dispersion relation, aka the relation between energy versus the momentum k, or the wave vector k, if you call it. So the very fascinating things that the physicists found immediately from just by using a very simple tight binding approximation is what you would call the Dirac cone. So the Dirac cone. So generally, when you talk about a massive particle in a classical regime, you know that energy is proportional to momentum squared, right? But whenever you have energy that is linearly dependent of a momentum, it means that the energy is a linear function of momentum. So what else has the linear relationship between energy and momentum? The answer would be light. So basically, when you write any sort of relativistic equation for a photon, you can actually write a cone like this, because the energy would be linearly proportional to whatever frequency you put in. Or if you talk in terms of like the by a wavelength and momentum, you could actually convert that into just like a linear relationship with a momentum. So with that, you can use the very same physics that you use with light with the electrons in the graphene. So people would say that, oh man, with this happy accident, you could have the electron that behaves like light, or you can say it is a massless electron, because the electron would travel ballistically inside of the graphene, because whenever you have this kind of relation, it means that the electron is effectively massless when it goes into this material. And the interesting thing about that is when things are so massless, then wow, what can you do? You would have a lossless translation. For example, you could transfer energy from one side of the town to the other side of the town using traditional electronics, right? Then you would have some sort of scattering, and then you would have a bunch of other stuff going on. But imagine if the electron travels as if it was a photon. That would be amazing, right? So yeah, that's one of the promise that that graphene introduces into. Like if you have a contact from A to B, the electron would literally fly ballistically from A to B with these relativistic sort of physics. So this is one of the most interesting physics inside of a graphene. So Novoselov and Gam didn't just Scotch tape pull the graphene out and then like, hey, Nobel Prize. No, what they did was they observed some really interesting two-dimensional physics using this relativistic motion of the electron. And this is among some of the first platforms that actually could host like theoretically atomically thin motion of the electron, where you can just have like one dimensional of the motion completely confined, and then the other two dimension completely free and then completely ballistic. So technically, electrons in graphenes behave like light more than a particle. So and then it didn't end there. The more interesting stuff is some of the mechanical properties. So people would say that the graphene is actually strong enough to hold an elephant on top of a pencil. So this is a little bit of exaggeration, because you know that the pencil would break first before the graphene, and so far we don't have like this kind of a sheet of graphene, and the next thing that would break are the the hand holding it. So technically, this is a little bit of exaggeration, but if you calculate the mechanical strength before it breaks down, the graphene could actually hold this, assuming everything else stays still. And another thing that's very interesting is right now people are trying to work on the wearable electronics. Like, for example, if you have clothes, imagine if you have clothes that could actually conduct electric circuit without, worrying about electrical wires being short circuited and stuff. So if you could actually make graphene part of the wearable electronics, that's also some of the dreams that a lot of people look into. And actually, there are people who look into integrating the graphene sheets as part of a complicated electronic structure inside of the shirt, or like products that you could just paste on and make a variable electronics that's very bendable and stuff. All right, so then let's say the question is, so we talk so much about graphene, but when is the age of the graphene? So that will be the question that you would ask. So General, sorry, that's not FET. And a FET made out of graphene was done in 2004 by Novel and Geim. They etched a Hall structure using the graphene and study the very interesting physics behind it. However, if the graphene was invented in 2004, then where is it right now? So people actually would have this like nice diagram about like, okay, so we would have a Stone Age in 100,000 BC, and then in 10,000 BC we would have Copper Age, then you have Bronze Age, and then Iron Age. So this is like the evolution of the materials that changed the world. Then you start having the Age of Steel, then the Age of Polymer, when we start producing plastics and stuff. Then this is where we are right now, the age of silicon, and then the age of the nano age, where people start looking into modifying the materials. So question is, when is the age of graphene? Why is it not here yet? So the thing is, before asking like where is graphene on the market, I would like to go back to why it doesn't exist yet. So so if you look at this picture, do you have any guess where this is? Hint, this is in California. So this is a valley, and there's a bunch of silicon in it, but it's not the Valley of Silicon, but it's the Silicon Valley. So this is basically the place where all kind of things were made into like all kind of silicon-based electronics were made. And silicon-based electronics is like, as you know, you create field-effective transistor, you create thermoelectric, you create a bunch of things, but everything has to be silicon-based. Why? The answer would be to create something that's globalized, to create something that's completely industrialized. It has to be based around a certain technology that's globally accepted. And silicon happened to be one of the first accepted technology that produced, the very first computer that are out there. So any kind of membrane, the iPhone you're using to watch this live stream right now, whatever computer you use, the gaming laptop, whatever, it all have this kind of stuff, a bunch of ones and zero that are like being calculated in the background. And that is growing from the fact that you could just machine the silicon-based transistor into a smaller and smaller kind of setup. And booyah, you would have a bunch of FET that used to look like this, but not anymore. Because you just machine it so hard that you reach the quantum limit where the things are so close together, it's almost atomically close to one another. Then, as you can see, you would have what you call the Moore's law, where things, how good is a computer is how tightly can you pack a silicon all together and machine it precisely enough to create things. So everything is based on this rock, silicon. So silicon is very useful. Is also the reason why graphene does not take over the world by the storm yet. Because if you go back in time at Bell Labs, the first FET was invented by Bodin and his team, and back in 1947. So let's trace back how the silicon came to pass. So back in the days, people were still hiring a bunch of people to switch, the wiring at AT&T in the United States. So in order to get one line transferred from one side to another, you need a physical person to switch things. So back in the days, even Newbohr said, who messed with the semiconductor is such a messy physics, it doesn't even exist. Who knows if it exists, right? I mean, now we all know that everybody hold like, trillions of semiconductor FET inside of your pocket, walking around like crazy. So same thing here. So so as the semiconductor first unveiled its potential in 1947, the first FET tech that hit the market was 1960, and these are some of the first commercialized computer. And as you can see, it looks almost like a refrigerator, and you would not use this kind of computer. And I'm not entirely sure how big is the RAM in this thing, but pretty sure it's pretty low, and the computation speed is pretty low. But back in the day, it was like pretty amazing that you can make electronic switch. You can make things to be either conducting or non-conducting. So that is what you call the semiconductor-based technology, and FET was one of the most selling point. And so since the beginning in the beginning of time of the Silicon Age, it started rising, and this is what you call the Moore's law. So the Moore's law said for every given amount of years, I think it's 2 or 3 years, the density doubles. So right here is a semi-log plot that like you have a log scale here, and then this is a linear scale. Then things go up, and all these little numbers are the name of the GPU or CPU, of kind of calculations based on different technologies produced in different countries. Again, everyone uses silicon globally. So everybody tried their very best to machine silicon in a nanoscale. So, however, Moore's law is predicted to be wrong at some point, because as you can tell, silicon is made out of atoms. So the silicon atoms, you cannot cut it down to be smaller than the atomic size. And then you would have some sort of what you call a quantum fluctuation. So there is a quantum limit and stuff to it. So if you base everything around the three-dimensional technology, things can be miniaturized to a certain level, because things that are so closely packed to one another would start interfering with one another, and then the electronic signal would actually have the fluctuation large enough that you can't even use it physically. So the age of graphene, back to our original question. So graphene is atomically thin. So if you can machine things, that is already two-dimensionalized. So then you have only 2 dimensions to work around, and then you would actually have like a stack of very miniaturizable material. So graphene was first invented in 2004. Then what's up? It's already 2020, 2021, right? So if you look up why hasn't graphene taken over the world yet, the YouTube channel would show a bunch of videos that said, why the graphene would be out there. So actually, a lot of people, a lot of tech geeks actually came out and predicted that eventually and very soon, the graphene is going to take over the entire thingy. But that has a big but. Like it has to be way better than the existing technology. So therefore, if you want to reinvent silicon, the entire world industry, imagine all of your best gaming like laptop company like Asus, they're not going to be happy if somebody in the market said, hey, let's switch to graphene, let's switch to two-dimensional materials. So things like that are still way ahead of us. And because in order to change something, you need something that are significantly better, to the point that people all over the world need to be able to change along with you. So the next topic that, as I outlined, is graphene and beyond. So the question would be, we talk so much about graphene, so what's beyond the graphene? So the graphene, as you can say, it has like this very nice direct tone. It has very interesting physics. It has tons of things going on. Electron moves ballistically. However, the biggest part in that is that this is like a two-dimensional metal. with like really high conductivity. But the fact that the conduction band and the valence band touch one another, meaning you always have, whenever you have a graphene, you cannot have a switch because it is in itself a very, very conducting material. So but silicon, for silicon-based technology, you can create silicon oxide, you can create metal contact, and you can use silicon as the semiconductor. So silicon-based technology has to be operated at a high temperature because you need to anneal things, you need to put metal contact onto it, you need to dope it, you need to make it oxidize in order to make like a practical material that matches with one another, to the point that like any new materials that would be integrated into the new technology needs to be what you call the silicon compatible materials, such as gallium arsenide and a bunch of other stuff. Regardless, we're not going there today. But yeah, now we have graphene, which is metal contact for 2D. So what's beyond graphene is we need to find what's two-dimensional, but also insulating and also semiconducting. So that's the research theme that was going on when I first entered the PhD program at Case. So this is a big deal when people jump into like, oh, okay, we made graphene, cool. What's next, right? So the next thing that we did was we tried to find the semiconducting version of the graphene, which the flagship material would be MOS2 if you work in the field. It's molybdenum disulfide. This is what you call the TMDs for short, transition metal dichalcogenase. So dichalcogenase is like whatever's in the group 6, and then transition metal self-explanatory. So whatever transitional metal does sit here. With two chalcogens, you have transition metal dichalcogenase, and magically, if you mix molybdenum with 2 sulfur, then it bonds in such a way that it creates a two-dimensional layer that is separated by a very satisfied polarization, to the point that you would have the van der Waals force interacting between each different layer. So you can see the theme here. They are trying to reproduce graphene, but on different kind of setup and on different electronical properties. And there's also what you call the hexaboron nitride. And as you can see, if you take a look here, hexaboron nitride is the insulator. But if you take a look here, this is hexagonal, this is hexagonal, this is also hexagonal. So all of these guys are just like materials that are attached together with the van der Waals force. So in traditional engineering, as I mentioned earlier, you need some sort of materials that have the matching, such as silicon compatible technology, as I mentioned. So if the lattice spacing, aka the crystal structure of the materials, do not match very well with one another, you would have this so-called defect that would actually destroy the bit, destroy the one and the zeros calculations that you need to do it very fast. And if you imagine, if you do calculation at what, like for example, your GPU speed like 2 gigahertz, then that means like in 1 second it goes like 2,000 million times, right? So if you have one every 5 times, then things go really haywire really quickly. Or even 1 in a million, that would go haywire in like milliseconds. So you need something quite literally perfect crystal-wise to not like ruin the calculation. So then to make a 2D FET devices was a major theme of my research back in the Case Western during my PhD. So why would you want to make 2D devices? So one of them is you can just peel them, attach them together, boom, you get the FET, right? In order to create a FET, you need semiconductor, insulator in the bottom, and then 2 metal contact on the side. So if you have graphene, you have hexaboron nitride, you have MOS2, theoretically you can make all kind of FET you want just by peeling things and attaching them together. And another thing is that you get really cool physics because electrons, as I mentioned, is confined in 2 dimension, and the graphene contacts are really good. And the most interesting things that people look into is the possibility of creating a wearable, bendable devices that are completely resistant to any kind of breaking. So unlike the traditional metals and stuff, it would not break because it has really flexible structure and very high plasticity constraint that it would be able to deal with all the stress that it was pulled into the materials. So my previous work was we were just looking into what you call the indium selenide. So I'm going to go this part real quick. So back in the days, me and my professor was looking at a theoretical paper that says that, hey, if you look at this paper, the density functional theory calculation, which calculates how well the electrons is being distributed, they predicted that the material should have like the mobility as high as 1,000 centimeters squared per volt second. However, when I started doing research, the best reported of this value of this material that you could exfoliate in 2 dimension, it was 0.1. So it was like 1 in a 10,000. So I was like, oh, okay, that's interesting. I'll try to make one. So I was trying to make one. And as I mentioned, so this is Mr. Van der Waal again. I put him everywhere to describe that there's a Van der Waal force between the layers. So to make one, it's quite simple. So this work was done by our NTU collaborator. What you can do is you throw indium and selenium at a very similar ratio, so 1:1, and then you bake it in an ampule at a very low pressure to avoid oxidation, and then the material would melt, and then it form the 2-dimensional stuff. So this doesn't look very 2-dimensional, right? But once you peel it, then you would get like this very nice flake that was sitting here. And then I make a very simple Hall devices. So again, I figure out in the end that the reason that people couldn't realize a good transistor out of it because people use the e-beam lithography technique and a bunch of technique that uses water. And based on my painful experience, I realized that these things don't do really well with water. I wrote it as part of a comment, and I also made that comment in APS March meeting, and some people did a DFT on it, and I'm really grateful. And they figure out that like, oh, okay, yeah, this material is a piece of shit when you have the water on it. But once you do all the process with all the water, for example, I put a TEM grid on it, and then evaporate contact, creating Hall device out of it. Turned out it was quite easy. Well, took a little while, but I could make like multiple contact of the indium selenide and then load it down into the PPMS, which is like cryogenics that could pump it down to a very low temperature and then cool it down. Pump it down to a very low pressure, then cool it down to a really low temperature with a dilution bridge. So we could go to theoretically millikelvins, kind of cold. So from there, we change the substrate and study the effect of the gate effect, and you can see that we have a pretty good on-off ratio. So the on-off ratio means when you say it's on, it has to read a certain current, right? This is your 1, and then when it's off, it has to read nothing. But then again, there's no such thing as nothing in the world of experiment. So the word nothing, generally it has something, which is the leak current. So the ratio between top and bottom has to read something high, and we were able to prove that this is some of the devices that could perform with the on-off ratio of 10 million kind of high. So basically we demonstrated the power of this tool, and then people actually took it seriously and then upgraded the technology in 2017 after I got my PhD. So people, I think in Cornell and other group, took the idea of putting the indium selenide into making a very, very good bioeffective transistor by strictly using 2-dimensional materials, using graphene as a contact, using hexaboron nitride as a nice little gate, so that you don't have any sort of defect. And turn out that they could create an extremely high mobility material. So in my case, I was the first to report like 10,000 centimeters per volt second. So that was like I don't know, 4 or 5 order of magnitude higher than the previously reported. So yeah, it got published, and then someone else took the idea and upgraded it, which I'm really grateful to see this. So you could see SDH oscillation, which is strictly 2-dimensional physics, operating in the very nice, pristine indium selenide run similar method, and they create a very nice 2-dimensional device that could prove very, very interesting 2-dimensional physics. So so as I said, the idea of like peeling graphite from here to here, it seems like very simple, and it seems like there's nothing there. But in fact, there is a big deal. Like whenever you transition material from 3-dimension to 2-dimension, generally you change the physics behind it drastically. For example, the band structure of the materials changes. For example, ammonium disulfide from multi-layer to a single layer became direct band gap instead of indirect band gap when it's a bulk material and other stuff. So graphene is also among one of the most drastic change when you go from 3-dimensional to 2-dimensional. And earlier this year, people, not this year, earlier, yeah, I lost sense of time. I'm still so fascinated with this paper as if it would happen yesterday. So that was during my time in Riken. So people put graphene together, and then you form this twisted magic angle where you could create superconductor out of graphene. It was pretty amazing, like because like that was I think it was 2019 when you say, hey, people probably ran out of tricks with the graphene. No, they're not. They just put graphene together, twisted by a very magic small angle, and then you form superconductor. And then once you miss that angle, the magic is gone too. So that's a huge deal. People do micro squid measurement in 2020 to figure out what is the interaction between layer. Why is bilayer graphene so special? Because if you put one layer of graphene, it's a Dirac cone. When you put 2 layers of graphene, it became a gap semiconductor. and then, but if you twist that, you create certain things. You twist a different thing, you create different things. And there are also a bunch of other interesting stuff. So here's also another thing that I would like to go over as this is like a talk for the IF, which is like very theoretical side of the physics. So I would like to go a little bit into the detail of what else of the cool physics that could happen in 2D. I kept saying cool physics, right? So there are also what you call the this is the work that we publish after I left, but the sample was made by Mr. Kasun, who's now Dr. Kasun. So basically when in the United States tradition, whenever a person leaves the lab, they train the next person, teaching them everything they know. And Mr. Kasun is very, very careful and very diligent with this kind of fabrication. And he could make like a device that, based on gating, you could actually tune what you call the weak localization and the weak anti-localization, which I'm about to go a little bit into detail. So before working about the weak localization and anti-localization, we should know about the Aharonov-Bohm oscillation. So we know from undergrad's quantum physics that when you have like the electron that travel and you have the magnetic field, then the electron that travels in circle around the magnetic field would pick up phase, and these phase would actually create either a constructive or a destructive interference based on the magnetic field that would manipulate the fundamental phase that goes into the material. So if you manipulate it correctly, it would create a strongly constructive interference. And then if you go way too far, then you start creating destructive interference. Then it goes back to constructive, then destructive. So this seems like an oscillation, because when you manipulate this path of the electron, when you have like a small ring here, then you would have the conductivity of the material that goes up and down as the magnetic field is changing. So so then again, this is just one ring. But in two-dimensional materials, you don't have one ring. You have tons and tons and tons of rings. So if you consider ensemble of rings, meaning you have tons and tons and tons of rings laying around in two dimension, then the propagation amplitude A of the different ensemble of the ring, you need to combine them based on the QFT approach, where you say that like, hey, okay, so if you have this propagation amplitude and then you have a mix of phase into the materials, then the probability of the electron to exist from R1 to R2 at a given time t is the summation of all the possible amplitude that is produced by the ensemble of rings. So from there, you can make some fundamental summations, and then the first term right here that you have is a classical term where the more it could travel somewhere, you sum it up square, you get the total conductivity. But then the second term is the interference term, where you have like AI and AJ interfering with one another. You have two rings that are sitting right next to one another, and then they could interfere. So again, in general, this term is usually sum out to be zero, because if there's no coherence at all, if you sum a random AI and random AJ, then you average them to zero, unless R1 and R2 are equal. So if R1 and R2 are equal, then AI and AJ from R1 and R2 would actually have the time reversal symmetry. So that you would actually create an identical phase and a constructive interference. So this would actually enhance what you call a backscattering, because it means that the more of these rings that forms in this way, this interference term would enhance the backscattering, because this time reversal symmetry create constructive interference. So but then again, so if you increase magnetic field, as I said, you are manipulating the microstructure of these interference. So if you tune the material to have a certain magnetic interference through this phase diagram, and you increase the magnetic field, so the magnetic field would break the time reversal symmetry. I said time reversal symmetry, R1 equals R2, create this nice little backscattering. So by increasing magnetic field, you're reducing the backscattering, meaning if you apply magnetic field, the conductivity should be increased, correct? Yeah, so this is one thing. So that means that like as you increase B field, then you would have less backscattering, meaning you should have higher conductivity, and then eventually you would have like this oscillation going on, because the physics here would actually have higher energy than the physics here. So that was what you call the weak localization, because things want to backscatter and it wants to stay still. Now, but if we have weak anti-localization, which in materials with a strong spin-orbit coupling, so the spin-orbit coupling would actually try to conserve the chirality, meaning that whenever you have like AI and AJ canceling one another, then you would actually have like the SP coupling, the spin momentum coupling, due to the chirality. So in turns, it makes that this term would try to mix in such a way that it would cancel one another. So if you tune the material to be in this regime, you would have the reverse of the weak localization. You have the weak anti-localization, where as you have more of these rings, you would have reduced backscattering. So the reverse would be true if you apply magnetic field. So if you apply magnetic field, you would increase the backscattering. So from this, you can see the materials of two regime. When you increase magnetic field and reduce magnetic field, you can either increase or decrease the tuning inside the materials in which regime would it operate. And in this work, we were able to prove that using this platform where you mix indium with selenium, it has like really strong spin-orbit interaction. However, you can fine-tune how many chirality that you could create by using gate voltage, how many carrier you can inject into the two-dimensional materials, and then you could tune the material to be either weakly anti-localized or weakly localized. And that paper was published in Nano Letter, and is among one of our most cited paper back in the lab. And yeah, And so this is one of them. So this is like one of the interesting physics. So you can see that. Recently we just had like a Nobel Prize talk about emergent phenomena. So this is a similar thing. Emergent phenomena came from things that are not quite like talking to one another, but they behave in a certain pattern. And then when you put them together, closely together enough, having them interacting in a certain ways, you create something large. You create something that completely change the regime at which you operate. It completely changes how you see these kind of materials and then see how they work. So another cool physics in two dimension is what you call the Landau levels. So my apologies if this is too basic or too advanced for a certain group of people. It's a little bit awkward, but to me, it's really cool because whenever you talk about 2D materials, you can't avoid talking about Landau levels. So Landau levels is what it happened when you put two-dimensional materials into a magnetic field. So generally, when you try to write the Hamiltonian of the magnetic field, so the magnetic field would have the vector potential. So if you apply what you call the Landau gauge, you can write the vector potential as the magnetic field multiplied by a Cartesian coordinate hooked up with the direction that is the other one. So if you curl it off this, if you curl this potential, you get the magnetic field B pointing on the Z direction. So this is important because if you can confine the material in two dimensions, you can see the full effect of the Landau level because the B field is always pointing upward, and there. By having that, you can rewrite the Hamiltonian, changing the potential, the kinetic term, right? But as you see that the kinetic term is shifted based on, what you know from fundamental quantum physics, and then this A is written as this guy. So then the amazing thing that happens here is that the momentum is actually hooked up with the position. So when you mix the position with the momentum, things get weird. So you try to separate them by using the separation of variables, and you can rewrite this equation of motion. Try your classic separation of variables technique, and it turns out that this vector potential is just a shift in a y direction. If you rewrite the Hamiltonian, then the potential term looks like this, and this is just a classic simple harmonic motion. So if you can just plug in the simple harmonic motion solution in, you could just find the energy as a function of n that goes up like this with the cyclotron frequency, meaning electron goes in circle in 2D, and then by tuning the magnetic field, you can actually have a different cyclotron frequency, and this has a split in the exact same fashion as the simple harmonic oscillator. And you have this amazing thing called the Landau level, where as you increase the magnetic field, you can shift the differences between you can change omega c. So as the omega c changes, you instead of having like a classical Hall effect where you have higher magnetic field, the charge curves. So by the charge curving, you would detect like a resistance. So the Hall resistance would go linearly depending on the magnetic field. But then once you increase magnetic field strongly enough in a low dimension, in a low enough temperature, then you start having this jump, which is called the quantum Hall effect, where you could theoretically measure the conductivity of a single electron, because literally a single electron trapped in this Landau level could be forced to cross the Fermi level, and then you could see this nice little jump here. So as the magnetic field is low, this is straight from Wiki. So as the magnetic field is low, you get a classical regime, and then as you increase omega c too much, then you start confining a single electron, and once it crosses the EF, then it starts conducting. Then that's how you get a single electron conductivity. So a lot of things happen, like for example, then people play around with the idea of what you call the edge state, and this is a big thing. Back in 2014, 2015, all the APS session would have what you call the topological matter discussion in nearly every single session out there, because when you talk about the topological matter, then you can't avoid talking about the edge state. So what is the edge state? So topological matter is the use of what you call the topology which means the signs of topos mean place. So you said that the signs or the mathematical description of any certain of a certain given property changes with position. For example, here, if you take a look here, electron moves in motion because it's bound to the cyclotron motion. So those are bound electrons, they move nowhere. But if you check out the edge, you can see that near the edge, what happened at the boundary condition? Well, electron could skip the edge and then it goes and conducts. So then if you take a look the classical paper back in 2005, this is like 1 year after the discovery of graphene. So back in 2005, people, the guys named Kane and Melee, which I've been rooting for them to get, the Nobel Prize. But regardless, they published this paper right in the very next year after graphene, saying that, hey, by the way, there should be a quantum spin Hall effect in graphene because if you theoretically you have two-dimensional materials, you think about enough physics of it. This paper has a citation of 4,000, 5,000. So it's now like one of the classic papers, and it has like a very strong scientific value, and people thought about that a lot. And this is Professor Chou Zheng in Stanford University. He is in particularly very interested in the topological phase transition of the materials by looking into materials where they don't have the direct cone at the center, but then the boundary condition of such material bend the spin orbit coupling bend the band structure enough that you would cross between the conduction band and the valence band at a different chirality, different parity. Then the particle going through such transition would try to preserve its own parity. For example, if it was an s electron, it doesn't want to convert to a p electron with which has like completely different parity. So you then would have what you call the direct cone near the edge because of the band bending and stuff. So that is where people started looking into a new class of materials, and then topology was the Nobel Prize winning idea in 2016. So basically, like if you talk about like the pretzel, how is it different from a donut and how is it different from a dough, then the answer would be if you are allowed to bend it, but you are not allowed to cut it or glue it, then you cannot form a donut into a dough, if you think about it. But then again, a donut can become a cup because a cup would have one hole. So those holes are what you call the Chern number, which can be strongly associated with the quantum physics of the Berry phase. So I would not go into the detail of this because it's getting a little bit late. So, but regardless, another thing that we could look into is the emergent phenomena, which just got a Nobel Prize. So literally, the electrons, they don't have mind, they don't have thinkings. So the same thing as these fish. So if the fish alone by itself escape the shark would outrun them. But if they form a school of fish, then you would actually, then each of them would instinctively obey the boundary condition with the things that allowed them forming this kind of structure that would trick the shark into not being able to chase a singular fish, therefore not getting any prey so long as they stay as a school of fish, like a very large thing. So this also explains a bunch of different critical phenomena, and so which is why this amazing work has been awarded the Nobel Prize winning award, because it explained a complete chaos and all kind of emergent phenomena. Another emergent phenomena was the work that I was doing back in Riken. So I did a postdoc in Japan, and some of the emergent phenomena is when you mix a really specific type of superconductor with a strong spin orbiting materials, then you can create what you call the Majorana fermion. And Majorana fermion is a particle that is massless, spinless, chargeless, and also its own antiparticle. So back in the days, this idea of Majorana fermion is proposed by this guy, Ettore Majorana, and it was heavily predicted to be the physics that described neutrino, because back then they thought neutrino was massless, but now we know that's not true. Regardless, people still look in the sky, trying to find the Majorana fermion in the air, like calling them the angel particle because they're so hard to find. Again, with the topological physics that happens around in two-dimensional materials, we were able to create what the quasi-particle that behave like Majorana fermions. But still, we need like a smoking gun evidence to prove it. But theoretically, it is very quite possible. And also, this is predicted to be among one of the platform for this quantum computing solid state physics that could actually like create a whole new set of platform to host a superconducting quantum computing platform. So I think I'm running out of time, so I'm gonna wrap up. So other cool physics is the Welle electronics, when you have like a spin of different Welle that you can distinguish between one another, and you may have heard about the term spintronics. So when you confine things in really low dimension, you can actually reduce the scattering on one direction. Therefore, any kind of readings that happen on one direction, for example, magnetic spin of the electron that goes along one plane, or the chirality of the electron that orbits around one plane. So if you confine things into one plane, you can create a lot of fun ways to make use of electrons and the interesting physics in the 2D. So again, the platform of the two-dimensional materials are not limited to exfoliable materials, but you can also artificially create the plane where you put the different oxides with one another. One of the most common one is the LaOSTO, so lanthanum aluminum oxide and strontium titanium oxide. So here, by putting these two together, you would have a completely flat surface that could also host 2D electron gas. And when you could make 2D electron gas, this is work done by Dr. Miwasana. So the work is still ongoing, and he's really amazing if you go through his paper. And there's tons of work that's also currently going on in Thailand in 2D materials. Another person, if you talk about 2D materials, is Dr. Puntranon, who's also a NECTEC staff, and he works on a bunch of like graphene 3D printable materials. And also, if you look up the real graphene, I start the session by asking, hey, why hasn't the graphene taken the market by storm yet? Well, people do put graphene in the electrodes to make so-called the real graphene, which is like basically a portable battery that can have really high charging rate and also really low heating up rate. So it means that the contact with the graphene has really high thermal conductivity. So they use graphene to improve the contact of the electrodes inside of these cells to make them more conducting. And also Tesla is also starting a graphene battery like project. So the age of graphene may be quite far away, but maybe not really that far away. And also at Mahidol University, Dr. Kanchanabut also make perovskite solar cell. He also collaborated with Chiang Mai University. He used the two-dimensional materials to code two-dimensional form of the perovskite to do some interesting physics near the surface, so that the electron could actually transfer better. Because when you make a solar cell, you receive photon, right? So to extract the electron out of the photon, the better conduction, the more energy you're going to get out of one photon. So let's say if you coat it with certain materials, it can actually also protect the perovskite solar cell from degrading due to water, humidity, and the oxygen. And this is also another group that works in engineering, Professor Ali Javed. This guy, I highly recommend, because he always have like one of the weirdest publication out there that that's also published in Nature. so they have like really creative idea and how to make device out of it. And I've been following him since I was a master degree student, and his works were amazing. And it's really adapt really well with the age. And I hope one day I could be like him. But summary and outlook. We went over the 2D materials. It's a platform of atomically thin device, and it has really cool physics. It provide platform for bendable electronics and a bunch of wide range application, and potentially competitor against the Rhine of the Silicon Valley, and also maybe in a few years, you might walk around with graphene in your pocket, or even topological matter. All right. Okay. Yeah. I think that wraps up my talk. Not sure if I have thank you slide, but well, thank you for your kind attention.
All right. Okay. Whoa. I would say wow. All right. Okay. Thank you very much for a very wonderful talk.
Thank
you. Learn a lot from your talk. Well, to be honest, I'm not the expert on I'm not doing the research in this field, right? But from your talk, I learned a lot, and yeah, I do understand why you use the word cool, right?
Yeah, I kept saying cool physics a lot, but
you mentioned about cool, and then it starts to all right, okay, I see. What do you mean by the word cool? Yeah, right. But I note a lot thing here, but I don't know where I should start first.
Please go ahead, wherever.
Yeah, but for the online audience, if you have questions, you can put on the comments, and then I can bring your question to the speaker. But in the meantime, so I love the story that you tell us about how graphene discovered from the Scottish, right? That very, I would say that is very
happy accident.
Yeah, that kind of thing. Yeah, because they intend to do something else, right? Some other thing, but they accidentally discovered this kind of 2D material, right?
Mm-hmm.
Yeah. Very, very, I don't know. Yeah. And so, you mentioned that at some point that you went to Japan to do research, right?
Yeah.
Right. Can you share some kind of your experience doing research over there?
Oh, okay, sure. Yeah. So I think if I go back here to show a little bit of work at RIKEN. So
RIKEN,
in RIKEN, I was mostly making these the chamber for that could host the AFM probe, atomic force microscopy probe, along with the STM probe, scanning tunneling microscope. So the thing about scanning tunneling microscope is that you need to get a tip really close to the surface, create a quantum tunneling current, and then use tons and tons of piezo to control it atomically sharp, and you could get a reading on the surface. The problem with that is you can't do it on insulating materials, and a lot of topological materials are insulating to an extent. So therefore, we wanted to have like an insulating tip that works as well. And in the meanwhile, as part of my work with the STM, I also was the STM guy for this project where we put bismuth onto what you call the BISCO. So BISCO is a well-known superconductor. I think if I remember it correctly, I think it's a P-type superconductor. Then again, the theory predicted that if you put like a high spin-orbit interaction materials, so bismuth on top of the BISCO or any kind of the P-type, D-type superconductor, you could create a potential host for Mariana fermion. So in this work, we collaborated with the Shimamura sensei, and then other people from Tohoku to do the what you call the APIS, shooting light on one direction and then measure it at a different angle. And by doing so, you could probe the energy of the photon that escaped. Then you can make a dispersion relation that plot out exactly where the direct cones are. And then we used information of the direct cone and the Weyl arc to find the topological phase transition at different given growth condition. And why they do that, I probe it using the STM to extract the electronic properties out of it in comparison to the optical properties.
All right. Okay. Very interesting. So for this particular slide, you have also quantum dot there.
Oh yes, quantum dot.
You're also working on something with the quantum dot as well, right?
Yeah, right. Actually, we just recently got accepted for publication for a few things with the quantum dot. So so the main thing about coming back to Thailand is that so this kind of project costs like 3 million something
All right. Okay.
like dollars a year to run. But yeah, you could just grow it using electrochemical bath, and then I could still do the the low dimensional physics. For example, here I try to grow two-dimensional zinc oxide. So this was my first work done in Thailand, and it got published in the MDPI materials. And we studied the annealing temperature, the growth condition and stuff. And the things that we do back in Chiang Mai is also growing perovskite solar cell. And as I mentioned, perovskite solar cell needs a really good material that could transfer either electron or hole, but not both of them at the same time from the materials. Otherwise, they would mix. And then, you use the energy from proton to create electron hole. If they go together, they recombine and recreate the photon, then that's not a solar cell, that's an LED. So you don't want to do that. So what you want to do is you want to find a very specific material that would separate hole, aka hole transporting layer, and electron, aka electron transporting layer. So from there, we found out that by using low dimensional materials, which is like the theme that I'm interested in, could also enhance the ability of such material to have better conduction for electron and hole in particular. And that is the current theme of my research right now. So we work on the quantum dots to enhance the perovskite solar cells performance.
All right. Okay. So very interesting. You can do very exciting things with the cheap budget, right? Okay.
Yes. So when the budget is the issue, we tend to lean to more of the approachable thing.
Sure.
Then we take a step up whenever we're ready.
Yeah, sure. Well, if I understand correctly, nowadays there is like quantum dot technology available in the market already, right? It's like the television actually made from the quantum dot. Like I don't know what is the brand, Samsung or something. I don't know.
Yes. Samsung does have like the quantum dot technology. Actually, I wrote an article for QTFT the other day about quantum dots and how it's put into the television. Long things short, when you have quantum dot, you can create the quantum confinement effect, and by using the quantum site confinement effect, you could generally either confine it into a very sharp lambda, or a very broad lambda, or like a very high lambda, low lambda, and then that you can create a very crisp display of the color with minimal loss, because the crystal are so perfect. But then again, you still need the screen and filter technology to create a proper picture. So the nice thing about a quantum dot is you can make very small LED, put them really close together, and then put it as one of the pixel. And once you have the RGB, you're excited with the correct excitation, you get the light coming out nice and clean.
All right, very, very good. So, another thing is that you mentioned about Moore's I don't know how to pronounce
Moore's law, yeah.
Moore's law, yeah. And then, well, it's something to do with the silicon, right? The double of,
because people are still stuck in the idea of how to better machine silicon.
Yeah.
But then again, the physics would forbid it, because eventually you would get to the point where the Moore's law break anyway.
Yeah, that is the thing. So the question is, when we reach at the point, so well, some people say that we should replace it with like a quantum technology, something like that. But I don't know whether that, in your opinion, are we going to have like graphene technology come first, or the quantum technology come first? And I don't know.
That's a very tricky question, because the whole argument about the Moore's law and fabrication was used a lot before IBM declared the quantum supremacy. Now that the IBM declared the quantum supremacy, then again, it's completely guaranteed that quantum computing is going to be a thing, like in the very near future. The question would just be the time, but still, based on the physics of the quantum computing, it can only do a certain very specific things better than traditional computer. In a sense, we would still need a traditional computer. So then the question you ask would come down to, how would you interface the quantum computer with the with the materials that are on the classical side. So I would say if it has something to do with the 2D interface and stuff, then the 2D materials would actually have like the advantage of it, obviously. Otherwise, then silicon, which is like completely well engineered, is still pretty good. Still, again, the platform about the quantum computing is still not still, as I said, because right now the IBM one is the superconducting technology. But then again, you know that to transfer quantum bit, there are so many different ways. Like, for example, photon can also be a qubit. Then squid, also a qubit. A bunch of other things can be qubit. Even Majorana fermion, like you can actually use it as a qubit. Anything that has quantum information can be used as quantum computer. So the fact that the superconducting one came out first doesn't necessarily mean that it's going to be the last one. So right. So my answer would be, the technology is still changing, and it's probably way too soon for me to say much. But I would still think that by the time being, the superconducting one is going to do the same thing to the technology as the silicon did, because it's the first thing that was discovered, the first thing that was developed, and the first thing that's feasible. Then whenever the first thing's feasible come out, that's when the defining technology comes into play.
All right. Okay. So, well, another point is that about you mentioned about emergence, right? And then, well, I just learned today that actually this kind of 2D material also somehow connect to like a complex world or complex system as well, to the like a topological stuff, that kind of thing. That, well, very interesting.
Thank you. Anything with more than one thing, be it electrons, be it polariton, be it any kind of ton, or even birds, you can create some sort of imagined phenomena.
That's very interesting property of this kind of material, right? Because you can have like you may not imagine that you could have this kind of exotic property of this material, right? When you constrain it into like in 2D somehow, I don't know. Very interesting. Well, and then you also, well, I don't know. You mentioned about the sorry, there is
no problem.
The message that's coming in. You mentioned about somehow the research at NECTEC. About graphene, right? That is very interesting. I didn't know that there is the people working on this. There is a battery or somehow. Well, it's very cool, I think. Wow.
So disclaimer: the battery isn't from NECTEC, but the graphene ink is from NECTEC. It's approaching the market, and people are also like making graphene shirt. But then again, the problem with that is the industrialization with the idea is very dangerous, because graphene, they're very light and they're very soft. So once it gets into your lung, when you tons of graphene and you can't find where is what, because a single layer graphene is very transparent. You can tell, you can smell. It's so light. It's so very robust. Once it goes into your body, it blocks the lung like COVID.
All right, because you mentioned some at some point like a wearable device as well. Right?
Yeah, that's part of it. It's made of carbon, so it's also biodegradable.
Yeah, okay. I think that would be like a future technology to come. Anyway, and then another point that I'm very interested in is you mentioned about the Aronoff bomb effect somehow. You showed a picture of the ring somehow.
Right.
That's remind me somehow that I don't know, a long time ago I have read about the panda ring. I don't know, it's something to do with that. I don't know. There's a group of people working on this kind of ring that we call panda ring, and then they try to do something that I don't know. They might not related to this kind of thing. But anyway, just
I'm not not very related to that. When you said when you look into the Aharonov bomb effect, the one thing that I could relate to, and that's the one thing that I always teach my student, is the Foucault pendulum. So the Foucault pendulum is when you talk about when you mix the two eigenvalues together, one fast changing, the other one slowly changing, then you could actually observe some sort of like slow oscillation versus the fast oscillation thing, and generally that would be somewhat correlated to the Aharonov bomb oscillation as well, because you would have like the eigenvalue that's large, and also this interface between the interference between the electrons of different magnetic phases going at one another at a different time scale.
All right. Okay.
Well, that might be completely unrelated, but yeah.
Yeah, right. That's okay. So, well, another interesting point that I just Googled while you giving talk is that I actually I have heard this a long time ago, that actually, because the graphene is very wonderful to the material, right? And then, well, there is some research that actually you can deposit the graphene with like anything, and then you can get very good property out of it. Is that, I don't know. And then there is some kind of research paper that actually you can even put a bird-proof somehow.
yeah, right. The paper literally said you can throw shit at graphene and it would.
That's I don't know. It's a little bit ironic, but I don't know. Is it good or is it a bad thing?
Yeah, it's a joke among the researcher. You can literally put shit onto the graphene. Some people would try to dope it coffee, some really weird stuff. And they would observe like the conductivity change, change in the materials.
That very, I don't know. I just come across with this is kind of long time ago, and then it's very interesting. Anyway, so can you mention a little bit about your research at your Chiang Mai University, or your research group or collaboration that you have for there might be some students who are interested in this particular field?
Oh, yeah, of course. Yeah, so if you want to be a purist and do full like 2D materials, I highly recommend this guy at Suranari. We're also collaborating. So he's been giving me bunches of samples, and which I'm looking into. But yeah, he's the research group at Synchrotron is like very strong and very ongoing right now. And one of our collaborators is also Dr. Adison at NECTEC, and also Dr. Kajanabut, also one of our collaborators. So so our lab do things among this field, like 2-dimensional materials, low-dimensional materials, graphenes, and quantum dots, and solar cells. So that's what we do in Chiang Mai University, and we're also looking for and open for collaborators, and any students who would be interested in making a better solar cell for the greener technology, and or help me engineer the low-dimensional materials to suit whatever demands. Then yes, you guys are very welcome to join us.
All right. Okay. Well, I think it's about time. We come to the end of the event or the talk. I would like to thank our speaker again, Dr. Sucharit. Okay, and everyone who stayed with us roughly 1 hour here online. And then before we go, that you please complete the survey form for us. Actually, the link already put in the comment. All right, and please give your comment or your suggestion. We can look at that, and we can improve our activity next time. And then, the next month, and we're going to organize again the ETH Colloquium number 5. And please stay tuned with us. And then for today, thank you very much, and bye bye. Yep. Thank you very much.
Bye-bye. Thank you all for your kind attention, and thanks for joining us. Also, thank you, IF team, for having me.
Right. Okay.